I can't use a pointer. Oh, there you go. Okay, so this is a screenshot of the paper that was published by the GRAM team. GRAM is the IR spectrometer on Juno, and this is like a sample of the data that you see. And uh, so the data that I am analyzing comes from this very tiny region here. And the reason that we are only uh, uh, analyzing just like small set of spectra from this very tiny region is that um, is because Juno's uh, pixel position on Europa are not very tightly constrained. So, which means that the observational geometry parameters like incidence angle, emergence angle of your spectra or of your observation are not very tightly constrained. That is the reason that these pixel positions are so huge. And so most of the data has not been it has not been figured out for most of the data sets, but there is like this small set of data right here for which we have tight constraints on the observational geometry parameters. So that is what I decided to analyze first. And so there are, I think, there are four spectra here, and I'm working with the mean of these spectra, which is shown in purple points here. And I would like to point out that the data has very high SNR. So this is about an order of magnitude higher signal to noise ratio than Galileo's data of Europa from its IR spectrometer NIMS that was collected in the 90s. So yeah, so as my title alluded to, the analysis technique that I'm going to use is Bayesian sampling or Bayesian inference, sorry. And so if I thought I'd motivated by giving a toy model example. So this is a simple reflectance spectra of amorphosized grains. And so this is the equation which tells you the I over F, which is the reflectance, and this is Hapke's model. And so if you see here, so the green line is a simple model which has some standard where I've fixed the observational geometry parameters, and I'm taking an average grain size of 100 microns for the crystallized grains, and because my fitting analysis will involve the grain size and the phase angle of the observation, I'm showing it here. I'm showing the parameters for this model right here, and so this is my true model. So I have added noise to these data points and to this model and created this fake data, synthetic data. And so what you're seeing now is that if I try other samples or other sets of values of the phase angle and the grain size around this parameter space, then you can see that the models are different, and some models fit the data well, the others are not. And specifically the models that are highlighted in green do a better job at fitting the data than the red. And so this is the goal of the whole Bayesian inference methodology is to explore this parameter space and find the regions where the data is, where the models are fitting your data very well. And so, or in other words, the probability of the model is very high. And so you use algorithms like MCMC, Markov chain Monte Carlo, or nested sampling, and you can get a lot of samples that correspond to this high probability region, and then you can marginalize these distributions along specific axes that correspond to your different free parameters, and you can get distribution of the free parameters. So for example, if I marginalize this 2D distribution along the vertical axis, I can get a distribution for the grain size of grain size solutions. And similarly, if I marginalize along this axis, I can get a solution for the phase angle. And so this is the spirit, or this is basically the crux of the whole analysis, that you explore a parameter space that is defined by the free parameters that you set, and you try to get distributions of the parameters, and they tell you and then you can get the median value of the distribution and the plus minus 1 sigma uncertainty. So it will tell you how well the parameters are constrained. For example, in this case, the grain size has not been very well. The grain size has been very well constrained. The error bars are very low. Well, whereas you see that the phase angle is not very well constrained. So this is one of the major outputs of Bayesian inference. At the heart of all of it is Bayes' theorem. So this is the control mechanism, so to say, that tells the sampler whether a model is good enough to be or a set of samples are good enough to be selected. And so this is probability of the model given the data, and it is defined as this ratio here, where this term is the likelihood of the data given the model. This term here is called prior, which encodes our prior beliefs in or our prior information of the parameters of the model. So in most cases, we take this assumed it to be uniform, so we don't want to bias bias our analysis. So we consider the all values of the parameters within our parameter space to be equally likely. And then this denominator is the integration of the term at the top. And this is something called Bayesian evidence that you'll shortly see is useful for comparing models. So the two outputs that you get from this analysis, two main outputs, are first parameter estimation that I've already talked about, where you get distributions of the free parameters that you are fitting for. And so the likelihood function here is a simple Gaussian, where it's basically the exponential of negative chi-square value. So this is pretty intuitive. The better the fit of a model, the smaller this chi-square value will be and higher its probability or the likelihood. Then as I said, the prior probability is, or the prior probability function is a uniform function. So it's uniformly distributed between the bounds of the parameter space that you set. And the theta here represents the different free parameters. So in my analysis, these will be the grain sizes of different components in my model, the fraction, abundance fraction, the porosity of the regolith, and so on. So and yeah, and as I've already talked about, the second important thing that you get out of this analysis is something called Bayesian model comparison. So this is one of the strengths of this analysis method, where it gives you a metric to compare different models. So for example, I have two models, model 1 and model 2, and I want to evaluate their probability given the data. And so I will take this ratio, probability of model 1 given the data and probability of model 2 given the data, and you can break them down according to Bayes' theorem. And if you assume that the prior probability of the two models is equal, you're not biasing your analysis, then this basically boils down to the ratio of these two likelihoods. And this is basically the integral at the bottom of the whole of the Bayes' theorem here on top. And so this prescription basically gives you a way to compare two models, and I have used this in my analysis as I'll shortly show. So analysis of genom data of Europa. So to give you some background, I am trying to constrain the composition of the surface or the patch of the surface that I'm seeing in my spectra based on its water ice composition. And so both forms of water ice, amorphous and crystalline ice, that are dominant in our solar system have been detected on Europa. And this is because even though Europa's temperature is high enough so that crystalline ice is the most stable form, the radiation environment of Europa destroys the crystallinity and causes amorphization of crystalline ice. So there is a balance that is found. And the goal of our analysis, to reiterate, is to constrain the abundance of and grain size of amorphous and crystalline ice in the genom data, compare intimate versus linear mixing models' ability to fit the data. So there are two ways that different components on the surface or different materials on the surface on a planetary surface can be mixed. One way is that they are mixed intimately, so they are very closely mixed together, so that the total reflectance that you're seeing is a non-linear sum of the individual reflectance contribution from each component. Whereas the other case can be linear mixing, where the different components exist as discrete patches on the surface. So the total reflectance is just a linear sum weighted by the amount of area that each component, or the fraction of area that each component occupies on the surface. And so I also want to test which model works better, which mixing scheme works better. And then constrain the porosity of the regolith. So how fluffy the material is versus how tightly packed the material is. So yeah, so before I go into the genom data analysis, I want to quickly validate my framework again with some synthetic data. So the idea here is that I create this model which has some standard geometry parameters, and it is a two-component model with amorphous ice grains of 200 microns and crystalline ice grains of 100 microns, a filling factor, which is basically the porosity of the regolith, or sorry, how tightly packed the material is it's around 0.25. So this can go from like 0.01 to 0.52. And the SNR of the data is pretty high, 100 of 100. And so I create this model, which is the blue line, and then I create a synthetic data out of it, which has this constant SNR. And when I pass this synthetic data from through my analysis framework, this is the result that I get. So what you're seeing here are the parameter distribution of the 4 free parameters in my model right here. So the free parameters in this case are the grain size of amorphous size, grain size of crystalline ice, the fraction of amorphous size. The fraction of crystalline ice is just 1 minus fraction of amorphous size, so it's not a free parameter. And this is the filling factor, so how tightly packed the regolith is. And you can see that the distribution of the derived distribution are very precisely they precisely align with the true values of the parameters. And so this is great. But now we take this one step ahead, and the model is not, now the synthetic data is not perfect. I add some Gaussian noise to it, some scatter. And so what the model on top has an SNR of 100, so the scatter is very difficult to see, but the model at bottom has an SNR of 10, so I have reduced the signal to noise ratio, so the scatter is more visible. And here I've summarized the results. So you see that for the intimate mixing model, which is the true model from which the synthetic data was generated, the result is still pretty precise. So it's detecting it's constraining the parameters very well for the 100 SNR case, and also for the SNR 10 case. So the results are pretty well. Even if I decrease the SNR by 10, the results match very well, and they are very close to the true values. And here I've also shown what happens if I analyze this data with linear mixing model, which is the incorrect model. And you see that the linear mixing model, although it spits out some results, its evidence is much lower than that of intimate mixing model. So what you're seeing here is the ratio of the evidence of intimate mixing to linear mixing model. So the higher this number is, the more the intimate mixing model is preferred. And so here you're seeing that it's preferred at a 20 sigma level. So this value basically can be converted into a sigma preference, where anything greater than 5 sigma has a very strong, it indicates a very strong preference. And so for SNR 100, this is very high. And even if I decrease the SNR by 10, by a factor of 10, it still prefers the intimate mixing model. And so this basically is an example to show how my analysis works. And it's a clear validation for this on the synthetic data. So let me then now move on to the analysis of GRAM data, which is the key thing. So again, the free parameters are the same: grain size of amorphous size, grain size of crystalline ice, number density fraction of amorphous size, and the filling factor. And these are the results. So let me slowly step through this. First of all, I would like to point out that I analyzed this data with 4 models. One is where amorphous and crystalline ice are intimately mixed. So it's a 2-component model with intimate mixing. The second model is where amorphous and crystalline ice are linearly mixed. So they are assumed to be present as discrete patches. Then there are single component models where I only consider amorphous ice and only consider crystalline ice. So first of all, if you look at the Bayes factor, which is again, the higher it is, the greater the preference for intimate mixing model. It clearly prefers intimate mixing model over the other 3 models. And so as having established that the intimate mixing model seems to be the more preferred one, and very strongly preferred one, I see that if we look at the results, you see that the amorphous, we find our results show that the mixture contains a very large number fraction of amorphous ice, which are of a very small average grain size. So this is 10 to the power 1.36, which is about 20 microns. And the amount of crystalline ice is very low, so just like 0.05%. And the grain sizes are very high. So this is around 600 microns. And the filling factor, which is the a fraction of the regolith occupied by material, occupied by the particles. So the lower the filling factor is, the more porous the material is. This value is pretty low. So the range that we explored was from 0.01 to 0.52, and it is very close to the lower limit. So this would indicate a very porous material. And what we wanted to test next was the robustness of our results to the noise, because we have reasons to believe that the noise is that our data has is underestimated. So the SNR that we have is very high than it might be much higher than it actually is. So what we did next is we analyzed this data again, but by inflating the noise. So we first tried by inflating the noise 20 times, so by equivalently decreasing the SNR by 20 times, then 30 times, and then 50 times. And what the bottom line is that even if you look at the case where the data has been where the noise has been inflated 50 times or the SNR has been decreased 50 times, the result here is very much consistent with what I was getting originally, right here, and it stays consistent throughout the noise inflation, like different cases. And again, the intimate mixing model is preferred over the other three models, although the degree of preference decreases as we increase noise, which is intuitive. But even at the extreme limit where we increase the noise by 50 times, intimate mixing model is still preferred over the linear mixing model at a 4 sigma level, and over amorphous and crystalline ice at 20 sigma, greater than 20 sigma level, where anything around greater than 5 sigma indicates a very strong preference. So now we move ahead with the conclusion that the intimate mixing model is the preferred mixing model. And so if you look at the best fitting solution for this model, it looks something like this. So this is the maximum likelihood solution for intimate mixing model. And you can see that there is clear mismatch in certain wavelength regions where our simple model that only has two kinds of water ice is not able to fit the data. And so this points to the fact that there are missing ingredients in your model. And we know that because there are hydrated acids, salts, oxides, and many other things that have been found on surface of Europa. But there are two reasons that we don't have those components in this model, in this analysis. First of all, this was meant to be a simple analysis to illustrate this Bayesian inference methodology. So we did not want to include too many components in our model. And secondly, and most importantly, the refractive indices or optical constants or opacities, whatever you want to call it, for all the other materials that you want to put into your model, which basically govern how they are absorbing light at different wavelengths, they don't exist for the wavelength region that we are interested in and at the temperatures that we are interested in. So in 2 to 5 microns region and at cryogenic temperatures of around 100 Kelvin, which is the condition at Europa, we don't have optical constants of hydrated sulfuric acid, hydrated salts, oxides, and various other things that have been already detected, spectroscopically detected on the surface of Europa. So that is the next page of the project, where as we get these new optical constants, we will incorporate them into the analysis. And so conclusion, most important conclusion is that our analysis points to the intimate mixing model as the most favored model. So where crystalline and amorphous ice grains are very well mixed together with a very high number density, a high number fraction of amorphous ice, which are very small, 20 microns, and very small fraction of large crystalline ice grains. And how do our results compare to the previous analysis? There is very good agreement. So first of all, the paper that published the GERAM data on Europa, whose screenshot I showed in my second slide, they did a very preliminary analysis where they used the strength of absorption features to figure out whether the data shows amorphous or crystalline ice. And they found out that the data that comes from the northern hemisphere, where our data also comes from, has predominantly predominantly amorphous ice signatures. And so that agrees, our results agrees with them. Then our results are also consistent with the radiation flux analysis by Nordheim et al., who basically calculated the electron energy deposition on Europa. And this is a map from the leading hemisphere of Europa where our data comes from. And you see that our data is actually precisely from somewhere over here. And it comes from a region where there is significant radiation processing, and more radiation processing means more amorphization of water ice. And so we would expect this area to have amorphous water ice. And finally, our results also correlates very well with this empirical relation that was observed from the NIMS data, where you see that the regions on Europa where sputtering rate is high, have higher grain size. So what is sputtering rate? Sputtering rate is basically uh, it's basically the rate of bombardment of ions on Europa surface, which cause destruction of the physical nature of the material on the surface. And so the region where sputtering is very high, where the surface is getting bombarded very much, the smaller size grains will get destroyed very quickly. So you would expect those areas to have larger size grains. And so vice versa, in regions where sputtering rate is low, lower size grains will survive. And so if you look at the bottom map, this is a map of the sputtering rate of Europa. The region where our data comes from, which is over somewhere here in the leading hemisphere, the sputtering rate is very low. And so you would expect the smaller size grains to survive here and to be visible in the data here. And this is basically what this correlation is showing. And our results are consistent with this empirical correlation that has been found. And moving on, another important conclusion of our result is that the data is not able to, the best fitting model is not able to fit the data at certain wavelength regions, like I showed in the previous slide. And so this might indicate presence of other materials that we have not put into our model. And finally, the porosity of the regolith that we find is very low. So it indicates a very light, fluffy material. But I would caution against this conclusion, because the main effect of porosity, the porosity parameter, is to increase and decrease the absolute reflectance of the data. So the actual values of reflectances. But I don't know if you have noticed. Sorry, I didn't point it out. But we are working with normalized data, because this is the data that was published and supplied to us by the Juno team. And so the effect of porosity parameter is kind of washed away. So even though our analysis indicates a very low value for the porosity parameter, we are not very confident in that. So yeah, so this is the total results from my analysis. Sorry for just speeding through this, but the paper is going to come out on arXiv soon, and it's going to be a very detailed paper. So please go read it and come to and ask me any questions you have. Thank you.
Yeah, thank you, Vishal. So we have time for a couple of questions. We have Abhinav.
Quick question, Ishan.
Yeah.
Great talk. How did you get the 0.52 upper limit on your filling factor?
That is a very good question. So I did not have time to get into the exact range of these priors, but for filling factor, the 0.52 comes from it was described in the book from where I got this model, and from what I understand, if you increase the filling factor to beyond this, so basically you are making your material tighter and tighter, it will be difficult to ignore the diffraction effects after this limit. So the materials will be basically so tightly packed that you will need to take into account the diffraction that is happening in between their spaces. And this model is only a geometric optics model, so it does not involve that as of now. So yeah, so you cannot take it beyond 0.52. So that is where the upper limit comes.
Thank you.
Yeah. Any other questions?
Did you guys see my hand raising?
Yes.
Can I ask a question?
I don't see why not, YJ.
Okay. So well, thanks for the presentation. Well, I think it's great. So maybe I just have missed, but what is the importance to finding out the mixing ratio between amorphous and crystalline ice in Europa?
So, I mean, the idea behind So the goal was basically to see whether our as I showed, like towards the end, the results that we have. So there is a broader trend of the results that have been found from Galileo and like other spacecraft missions or ground-based analysis. And so the goal was to just basically see whether this is consistent with that. So because amorphous and crystalline ice, the dominance of one over the other very much depends on the local conditions of the area that you're analyzing. As I said, like the more radiation processed an area is, you'll expect more amorphous ice to be found there. And so it relates to that. So we just wanted to see if that is we can tell something about the fact that if indeed finding more amorphous ice, maybe it tells us something about the degree to which this material has been processed. And why we are interested in finding out whether some area is more processed than other is because you want to, from an astrobiological sense overall, you want to figure out where the material is fresh. So if it's less radiation processed, you are inclined to believe that the material is fresh. And so if you further analyze from that area, you can basically like if the material is indeed being deposited from the subsurface ocean, so if it's coming out, extruding out on the surface from the subsurface ocean, if this is a good way to tell whether the material is fresh or not. So yeah, so that is like from the top of my head, that is one of the motivations to figure out why when there is more dominance of amorphous, like why one dominates over the other, or which one is the dominant component. Yeah.
So which one prefers a fractured surface more?
So like, as I said, if the material is more fresh, it will not be processed. So it will not, and processing basically converts crystalline ice to amorphous ice from what what we understand from our laboratory studies. And so if a material is fresh, we would expect it to be dominated more by crystalline ice. That is what I understand.
Okay, thanks.
Yeah.
So Ishan, you have a question here in the chat.
Okay.
I don't know if Sam wants to read it, or if Sam wants me to read it, or if you just want to read it.
Yeah.
But
Sorry,
but
the submissions are for quicker than that sputtering rate. Okay, I will have to read about this carefully, and maybe Sam, you can just mention what you're talking about.
Yeah, so sublimation is dominating seemingly at the lower latitudes that you're
right.
But that's going to be
you're not coming through clearly. Can you say that again?
Yeah, that's why I just sent it to the chat.
Oh, okay.
It's essentially, is it consistent with sublimation at these latitudes? I would assume might lend it to more crystalline ice particles. But I'm not entirely sure. I would suggest just double checking the hobby work as a suggestion, not as a. It's is it consistent with that as well? This is really interesting.
Yeah, I'll have to think about this more. Although my data does come from like 40 degrees latitude, but I'm not sure if that is like a hard thing. But yeah, I'll think about it more, and let's talk about this offline.
One becomes dominant, or sputtering does become dominant higher up.
Yeah.
But I'm not sure. It's just, I would suggest that could be something worth looking into.
Okay. So any other question? Okay. So we should moving on to the next presentation. Thank you, Sean, one more time.
No problem. Thanks a lot for listening to me.
So we have the second presentation by Nate today.
oh wait, no, don't do that one first. That one's a surprise. All right. Is my talk coming through?
Yes.
All right. And is the little presenter thing over here in the way, or can you just see my talk?
We see your slide.
Okay, great. All right, so I'm going to be talking today about work that I've been doing for the last couple of years, trying to describe the distribution of haze in Pluto's atmosphere. So I'll be using data taken by the New Horizons spacecraft, which flew by Pluto in July of 2015. And the haze which I'll be talking about, you can see pretty clearly here in these beautiful bands. So these are distinct haze layers which extend up to 80 kilometers. And this is taken by the LORRI instrument, which was the high resolution camera aboard New Horizons. I won't actually be talking about these layers, but this is a really unique feature, even in the outer solar system with other hazy bodies like Titan and Triton. Even among some of these famous haze bodies, this one is a really unique feature. So first off, what do I mean when I say haze? Because there's a lot of other stuff in the solar system which scatters light off the atmosphere. We just heard from Ishan talking about sputtering. You can actually get that on the moon. You get a very thin atmosphere of potassium and hydrogen from sputtering. And then Enceladus in Europa, or maybe Europa, we have outgassing from geysers. But haze is formed, it does not come from the surface, it doesn't come from the internals, it's formed high up in the atmosphere. And the haze at Pluto is very similar to the haze at Titan, which is probably the most famous haze in the solar system, which gives Titan its beautiful orange color. So UV photons and high energy charged particles break down methane and nitrogen high up in the atmospheres of both Pluto and Titan to form radical particles. These will then combine and form together to form larger and larger particles, and these will continue to grow as they fall out through the atmosphere. And at both Titan and Pluto, these grow by fractal agglomeration. There has been some work to test whether or not these grow by spherical growth, condensation, but it seems that these grow via fractal aggregation. So that's what we'll be dealing with. We'll be dealing with these organic rich gunk with some nitrogen thrown in there. So I'll talk about the data. I'll talk about the radiative transfer, how we're actually going to look at the real signal, and then get to the real meat of it, which is trying to describe how these particles are distributed in Pluto's atmosphere, which can tell us something about the dynamics of Pluto's atmosphere and the nature of the particles themselves. So now that we have an understanding about haze, what's the data that we're going to be talking about? We're going to be talking about data which comes from off the limb of Titan, off the limb of Pluto. So all of the observations are not going to intersect the disk at all. We're only looking at stuff, if you can see with this blue cross over here, we're only looking at pixels which are completely off the disk, which completely go through the atmosphere, never intersecting the surface. This is called the limb scatter technique. And I have a side view of that real observation there. You can see that sunlight interacts with a particle at a distinct height and then is scattered into the line of sight. So this requires a totally different system of radiative transfer equations than what is typically done for bidirectional reflectance or happy parameters, because we are obviously looking at an emission angle of greater than 90 degrees. And these angles that I keep referencing, phase, incidence, emission. The incidence angle is the vector from the sun, or the source of illumination, in this case it's the sun, is the angle from the source of illumination to the target, in this case the haze. And the emission vector is the vector going from the scattering event, again, the haze, to the observer, New Horizons in this case. And then the phase angle is the angle between those two vectors. All right. So that's what we'll be looking at. That's the actual data. That's the actual brightness that we'll be looking at, is this limb scatter data. So where's the data coming from? It's coming from the MVIC instruments, coming from the multispectral visual and infrared camera aboard the New Horizons spacecraft. This was a imaging camera with 7 independent CCDs operating from 400 nanometers to 1,000 nanometers. It operated in time-delayed integration mode, which allowed the New Horizons team to grow arbitrarily large images and with arbitrarily large SNR. It had several panchromatic filters, but we'll be only using the color filters because we're also looking at, there is a lot of composition, the composition and the size of the particles impacts the scattering of the scatterings that we observe, which is also controlled by the wavelength of light. So all of this needs to mesh together in our explanation. So we're only using 3 of the color filters though, because the methane filter is redundant with the near IR filter, and the methane filter has a much lower SNR. So we're using near IR, red, and blue. And there on the left, you can see the observation that was actually taken, the series of observations that were taken by the New Horizons spacecraft as it flew by. Great, so that's the data. Problem with the data is that there's this really bright off-disk glow, which we can see here in these stretched images. On the left side of the image, on the left side of this figure, I have Charon. Charon is an airless, hazeless body. And yet, when we stretch the image, you can see that there is this really, really bright halo or really bright glow around the disk of Charon. So this can't be coming from any kind of scattering in the atmosphere. This has to be coming from an instrument effect. This has been identified in a previous paper. This is a similar result. This is a similar effect seen by Lori. We're not really sure what this effect is, but whatever it is, we have to remove it because that's where a lot of really good data is, especially at the lower SNR levels, which are going to be important for our backscattering component of our phase curves. I'll highlight this later when I actually show a phase curve. But backscattering is, what we're looking at right now is a backscattering event where light is coming at a low phase angle. So the way that we remove it is we take these transects around Charon, which you can see here in the leftmost image. We keep track of all those images, all of those pixels, how far off the disk those pixels are, and we also keep track of how bright the pixel on the disk is. And we know what the point spread function is for the MVIC instrument. So we combine all of that into this 2-dimensional equation, which I found through experimentation. And as you can see to the right, we have our Pluto transect limb data, we have our Charon transect limb data, and then we have a fit to that off-disk Charon data. And you can see that we're able to fit that off-disk Charon data really well. And that's what we're going to subtract from the Pluto limb data to get our phase curves. So now our data is completely corrected. Now we need to limit the data that we're actually using. So first off, we're only going up to 500 kilometers. This is the area where we believe haze production begins, so 0 to 500 kilometers. We're looking at a very low incidence angle range near the terminator, but not at the terminator. This will help us to reduce any secondary reflections from the ground. It also gives us a more consistent data set. And then most importantly, we're limiting the latitude and longitude range. So this is, you can see here on the disk, the sub-tangent points that all these profiles make through the atmosphere. Looking through the entire data set, I found that the sub-tangent point, the geographic location of where the profile is going through the atmosphere had the biggest effect on the variability of the data, so we limit that. And then finally, we just limit the selection of Pluto's data to pixels near the brightness of Charon's limb data. That way we can maximize that Charon off-disk glow correction. All right, all that's done. We have our data subselected. We can finally talk about our actual phase curves. And here are our phase curve observations. So we were able to get 8 observations at a range of phase angles from 15 degrees to 175 degrees. The low phase angle observations are the backscatter component. The high phase angle observations are the forward scattered component. And these tell us two totally different things about the way that the haze is scattering. You need different sized particles in order to get these different unique features. So you need a not insignificant amount of backscatter, which we see here, is caused by small sized particles, which can scatter isotropically. Isotropically scattering means that it scatters the same forward and back. However, you can see that we have that large forward scattering peak. Well, that's indicative of large size scatters, and that's in the Mie regime. So we need to have, whatever our distribution is, it needs to both explain this forward scatter and this back scatter component. Any description of our haze also needs to explain these three filters equally well. Due to the limited nature of the talk, I'll only be showing data for the MVIC red, but in trying to find the best fit description, I'm using all three of these wavelengths. They have to fit the data equally well. And then you can see what our haze profile looks like as we go up into the atmosphere. And any description of the haze also needs to explain that variability in altitude, how the backscatter and the forward scatter components both fall off as we go higher and higher in the atmosphere. Okay, so that's the thing that we have. How do we explain it? We do that with these radiative transfer equations, which I described earlier, is the limb scatter technique. What I'm actually showing here is actually bidirectional reflectance, but I think that this is still useful for explaining how we simplify this radiative transfer equation. So we're only looking at that first component where light enters the atmosphere, scatters off of a haze particle, and scatters back into our beam. All of these secondary, tertiary scattering components we're able to ignore because they contribute so little to the I/F signal. We're also able to ignore this source term or any brightness that intersects the disk. So if a photon misses any haze particles, hits the surface, and then comes back to the New Horizons spacecraft, we're able to ignore that because of the limb scatter technique, because our line of sight is not intersecting the surface at all. The second way that we're able to limit this, this radiative transfer equation is by removing the gaseous component. So what I have here is a figure of the UV solar occultations taken by the ALICE instrument on the New Horizons spacecraft. And what you can see is the amount of gaseous components and haze in the atmosphere. Well, the dominant gaseous components are nitrogen and methane. But this amount of nitrogen and methane, even at the lowest part of the atmosphere where the abundance is at its highest, only accounts for 10 to the negative 4 in our brightness. So we can ignore the gaseous component. So all of our brightness is that we observe from the limb scatter is due to scattering due to aerosols. That means that our phase curves are completely produced by these aerosols, and we can uniquely describe the aerosols without having to worry about any of these other components muddying the waters. We can further simplify that because the I/F is the brightness, the total description of the brightness of the particles is based on the number density, the scattering cross section, the phase function, and how far away our observation is actually taking place. While that all affects the total brightness, the only term which actually affects the brightness as a function of phase angle is the phase function. So we can collapse all of that and just say that the observed phase curve is proportional to the phase function. And the phase function has a lot of, can tell us some really interesting things about the nature of Pluto's atmosphere. So again, phase is the angle between the incidence and emission vector. It comes from this actual description, how we call the phases of the moon. And the first widespread phase function was in 1941, the Henny-Greenstein phase function used to describe scattering of dust particles in galactic material. There are a wide range of phase functions that are used to describe different sized particles, different shaped particles. What I'll be using is the fractal aggregate phase function produced by Tomasco et al. To describe scattering within Titan's atmosphere. And the important components of that phase function are the fractal dimension, the number of monomers per aggregate. So, how many of these little tiny monomers, these little balls, are stuck together to make this fractal aggregate. The index of refraction of the material, so this tells us what it's made out of. The size of the monomers, which is given here by the radius of the monomer and the wavelength of the light interacting with it. That's why we need to make sure that any of our phase functions that we try, any of our particle descriptions that we try, has to fit all three of our wavelengths. So we assume that for the complex index of refraction, we assume that it is the same as Titan's haze, and we assume a fractal dimension of 2. I will talk about at the end why this might not be the best assumption, but for the time being, we'll just assume a fractal dimension of 2. This is the most widely tested and verified fractal dimension for this code and for most fractal aggregates. And then finally, we assume that the monomer size does not change with altitude. So while the aerosols themselves will continue to grow, the individual monomers that are formed high in the atmosphere by UV photolysis, once those form, those don't change. Okay. So the different distributions of particles wrap into the phase function to give us different phase curves. And this is the main result of this work, to try to describe how well these distributions describe our phase function, right? So what I mean by distribution is the amount of small particles, intermediate sized particles, and large particles. How many of those do we have, and how are those distributed? So I tested 4 different distributions. The first is a monodisperse, which literally means the entire atmosphere is described by a single particle. A log normal distribution. This comes from work that has been previously done by Peter Gao. A power law distribution, and finally a bimodal distribution, which is similar to monodisperse, except we're now using 2 characteristic particles. And what you can see in this example, this is at 20 to 40 kilometers using the MVIC red data, is that a monodisperse and the log normal distribution are not able to very accurately describe our observed phase curve. We're able to get the right order of magnitude, but we're not able to capture simultaneously the not insignificant amount of backscatter, which again is indicative of the small size scattering population, and the very steep forward scattering nature, which again is indicative of large size scatterers. So monodisperse and log normal are not able to describe that. However, a power law and a bimodal distribution are both able to simultaneously describe that phase curve. So the distribution of particles in Pluto's atmosphere comes from either a bimodal or a power law distribution. Now I'm going to talk a lot about the power law distribution because that has fewer free parameters for us to work with. And it also, and then I'll also be comparing that to the published data from Gao. So what you can see over there on the left is another statistic for determining how our quality of our fits. This is our R-squared statistic, and you can see that at every altitude we fit the observed phase curves better, except at about 150 kilometers. 150 kilometers is also the area where we have a very sharp transition in the nature of our phase curves. So we go from highly forward scattering, as you can see from the power law exponents, to a nearly isotropically scattering atmosphere. This happens to be at the exact same altitude where the transition occurs from precursor material to haze material, which was predicted by Bertrand et al. 2017, which used GCMs to predict the abundance of precursor and haze material. So, two possible interpretations for the nature of Pluto's atmosphere. The first is a power law. What this means is that if we have a power law distribution of haze in Pluto's atmosphere, that must mean that we have a very large abundance of small size scatterers, which gives us our not insignificant backscatter component, and a good amount, a not insignificant amount of large size scatterers. So you can see how those two particle size distributions compare with the previously predicted results from Gao et al. For a log normal distribution. So our coagulation rate, in order to get this kind of distribution, our coagulation rate must be lower than our fallout rate, because we only have, our small size scatterers are only increasing as we go to lower and lower altitudes. Which means that these small size scatterers are not being removed through production of larger size scatterers. They're just continuing to descend through the atmosphere. So how do we get those small size scatterers? One potential explanation is a higher charge potential. So again, this was investigated by Peter Gao, and they predicted a charge ratio of 30 electrons per micron. If we have a higher charge to particle radius, that means that our particles are not able to stick together so easily. That means that our smaller particles will not as readily form larger particles. This was also tested. This was tested in Peter's paper again, and you can see in this bottom figure that a higher charge to particle radius ratio actually fits the observed solar occultation observations better. So this seems to hold. Now, if we have a higher charge to particle charge ratio, and if our coagulation rate is lower, how are we able to get large particles? Well, if our sedimentation rate, if our fallout time of the particles is significantly low, they fall out very slowly, we should be able to form larger and larger particles, even if the smaller particles don't want to stick together so readily. And we can actually achieve this by lowering the sedimentation velocity, as you can see in this figure here. And with a fractal dimension of 1, we actually have a sedimentation velocity significantly lower than the eddy diffusion rate. So this is one way for us to get that abundance of small sized particles while still having our larger particles. This is not the only explanation though. Another explanation for the unique scattering that we observe is bimodal distribution. So instead of what I'm putting forward, what I'm suggesting is that instead of two different populations of fractal aggregates in the atmosphere, we could have two completely different haze particles. If you remember from that figure before, which I can go back to, we have that turnover from precursor material to hazy material. This all occurs at 150 kilometers, and this also, that 150 kilometers number is right where the condensation environment happens, which you can see in this figure here, where all the gaseous components start to condense out. So what I'm suggesting is that we have one particle type which condenses from 5 nanometers to 50 nanometers and grows from 500 to 150 kilometers. Once you get below that 150 kilometers, though, where condensation stops, those particles cease to grow. You have a second population of particles which continually grows all the way from 500 kilometers through 0 kilometers through fractal agglomeration. These never condense out together, and they just continually grow. After they get below that 150 kilometers, that becomes the dominant scattering population, and that's what produces our very large scatterers right at the end. So that's what I have, and I think I saw a question pop up, so I think I'll go ahead and stop there.
Hey, thank you, Nick. Anyone have any question?
Are you going? Oh, it was Knock. Yes, I was going to conclude soon. Thank you, Knock.
Yeah.
Great. I'm glad I proved everything about Pluto's haze.
One quick question that is not related to the presentation. So is that the flag of the behind you, the broad Pluto of the steel?
Yes, yes it is.
I love it. That's pretty cool.
All right. Well, thank you, everybody.
Yeah, thank you, Nick, again for the presentations.
All right. Lucas, oh, you have a clapping thing. Okay, I see.
So are we ending at 1:15 then? Is that right?
That sounds like, yeah.
Yes, that's about right. Well, I think Nick's work is, I didn't want to ask any questions because I don't have any because I've been involved in the work, but I have to emphasize before we go that these are not easy data to work with. And of course, Pluto's haze structure is turning out to be very unexpected. So it's definitely a tricky problem. And I think this is, once the paper is submitted and through the review, I think it's going to have a pretty substantial impact. So.
Excellent. Thank you.
So I'm going to sign off and figure out why my video from this morning's class isn't uploading on Zoom. Probably because 1,000 other classes are doing the same. Anyway, cheers.
All right. Have a good day, everybody. Have a good week.
Yeah.
Bye-bye.
Bye-bye. See you on the view next week.
Bye.